Also, I would like to thank the organizers for inviting me. So what I would like to talk about today is fast algorithms for the one fair packing problem, and that's joint work with Paco Criado and David Martínez-Rubio. So what's this talk going to be about? So we are going to consider a specific optimization problem. In fact, we have some nonlinear objective function here, and we want to maximize this objective function subject to some packing constraints. And yeah, this problem occurs in many real-world contexts, and what I would like to do today is to specifically talk about the fast and distributed algorithm for solving this problem. So just a very brief overview. So I will first talk a bit about the one fair packing problem to provide a bit of context, and then I will talk about the actual optimization method. I apologize in advance, the proofs are a little bit technical, so I will confine myself to the key building blocks and how everything fits together in the last step. All right, so let's get started with a one fair packing problem. So given a matrix A that has non-negative weights, let's say the matrix A is a real matrix, what we want to do is we want to maximize the sum of the logs of the coordinates xi subject to this packing constraint ax less than or equal to 1, and the 1 here is the all one vector. On top of that, we have that the x should be non-negative here, but that's obvious from the setup. Anyways, all right, that's the problem that we care for and that we want to solve. In this context, typically an important notion is the notion of width, because it's some measure of complexity, and the width of the matrix A here is basically defined as the ratio of the largest entry of A divided by the smallest non-zero entry of A. The reason why I have introduced this notion is to basically say that we want to look for algorithms that are independent of this width. The reason for this is if you typically have width dependence, it means that you have some form of non-polynomiality in the parameters that we don't want here. That's the first thing that we care for. And the second thing that we care for is that we want additive epsilon minimizers to this optimization problem. So that's the very basic setup for today. Why should you care? Well, this problem naturally occurs in many different setups. For example, there is a certain setup of whatever natural means here, fairness axioms, and if you consider these axioms, then this type of packing problem arises as the natural optimal solution. This type of setup also very naturally occurs in the context of Nash bargaining solutions, or when you want to do resource allocation in, for example, data centers. People have used it in rate controller networks. That's more of an EE type of application where you have one channel, you have different senders, and you somehow need to spread the spectrum across these different senders. And more generally, there's many applications in game theory where this type of problem naturally occurs. Sometimes people also call this the proportional fair allocation problem. So that's just to give you a bit of a context where this problem naturally occurs. There's, of course, many other notions of allocations that you might care for. There's the standard one when you don't have the logs, that's just a linear objective and you have no fairness. Then there's things like such as max-min allocations, or also the notion of alpha fair allocation. So that's basically a generalization of everything before, yeah. Graph entropy, good one, yes, another one, yes. Yeah, so you see there's many applications, and that's why we care for this problem. All right. Having said that, let's have a very brief overview of what has been done in that space and what we are going to see today. So there have been quite a wide range of works on the setup. I'm just like summarizing some of the key results here that are important for the discussion today. So probably one of the earliest works is Beck et al. 2014. They basically give an algorithm that is width dependent though, and give you basically rho squared mn by epsilon. Then a little bit later, there's the first nearly width independent algorithm with n to the 5 by epsilon to the 5. The tilde here just hides log factors. A bit later, it was brought down to n squared epsilon squared, also again nearly width independent, but not quite. And then we have an algorithm for the primal, which is what I'm going to talk about today, which is basically epsilon n by epsilon. And you can also very naturally consider the dual problem. The dual problem has certain applications, for example, in linear programming. I think Paco gave us some time back where you look at the dual setup. And there we have the first with independent algorithm with n squared by epsilon. However, I'm going to focus on the primal algorithm here today. Yeah, so that's what we're going to do now. Just for reference, the cost of an iteration here is basically proportional to the number of non-zero entries in your matrix A. All right, let's talk about the algorithm. Let's start maybe with a very brief overview of what the key ingredients are to make this thing work. As I said, I will talk a bit about the building blocks, but we will not have the time to do a deep dive on each one of the building blocks. But then I will show you how everything fits together in the end. So a somewhat simple but quite important first step is a problem transformation. So we're going to transform the problem in such a way that we can basically make it width independent. Then a second step involves basically smoothing the objective function and adding a special barrier function. Things like this have been done before, and for example, in the context of the zero fair packing or the standard packing problem already before. Then another thing that we are going to do is we will have to truncate gradients for our mirror descent steps that we are going to do. The reason why you typically want to do something like this is because if you look at the mirror descent guarantees, that it depend on things such as the diameter of the feasible region if you project, as well as the norm of the gradients that you see. So being able to truncate them typically brings down complexity, and that's something that we are also going to use here. Something like this has been also been done before, and also in the context actually of the one fair packing problem, but the algorithm was an unaccelerated method that was actually the n squared by epsilon squared algorithm that we have seen beforehand. And last but not least, what we do is we basically use this concept of linear coupling, which couples together two optimization algorithms, in fact, mirror descent and graded descent, and that allows us to get an accelerated method. And that's quite a flexible framework, basically, to put these algorithms together. Mm-hmm. Mm-hmm.
Repeat the question.
Yeah, so I have to repeat the question. So the question was like in applications of graph entropy where you have basically an exponential number of rows, I guess, right? Whether the algorithm has any dependence on that. No. I mean, we see that the parameters go in later in the log factors. So you will have some log dependence on M, but not in terms of the number of iterations. All right, so these are the key ingredients. What you get in return is basically an accelerated first order method. The method is also distributed in the sense that if you consider each of the variables x, j separately, they basically only need to know the corresponding column of A and maybe global problem parameters, but nothing else. And you can basically run them completely independent of each other. The algorithm is going to be width independent, which is one of the key things here for us. And it's also deterministic. I mean, there's various stochastic setups also out there, but we care for this deterministic algorithms here. So that's a very high level overview of what the corresponding steps are. Now let's have a look at the respective steps. The first one is the problem transformation. In contrast to what people have been doing before, and by basically rescaling such that the minimum entry is equal to 1, we actually do rescale that the maximum entry is equal to 1. And that's quite nice here in this context. If you think about this, the objective function was log xj, like some of those log xj's. So if you rescale the columns here, it means that you have to rescale the primary variables by a multiplicative factor. Everything is in log, so it gives you an additive error. Since you care for additive guarantees, this rescaling basically does not do anything to your guarantees. That's the first step that we do. The second thing that we do is once we've done this, we reparameterize the problem to basically put it into exponential space. So the way of how this works is we basically define this function f hat here, which is basically the same function as before, except for that we plug in the e to the x, basically. The reason why we want to do this is because it makes the objective function linear now. So it's just the sum of the xi. You don't have the logs anymore. But of course, your constraints get now more complicated, and you now have this ax less than or equal to 1, and the x function here is, of course, coordinate-wise. So that's the second step. And now what you do is you basically regularize the objective function by creating a barrier function out of these constraints. special barrier function. In fact, it's not the standard barrier that you might expect here. It's not so important where the betas come from. The only thing that is maybe important to keep in mind that the beta does depend on the epsilon that you care for in terms of target accuracy, and also in terms of the question from before, the m does occur here in the logarithms. All right, so in fact, what you end up with now, if you do it that way, is an unconstrained minimization problem. Technically, we are going to add a box later, but for now, think of this as an unconstrained optimization problem. And this barrier function here that we see has a couple of nice properties. You might want to check out the screen on the left. I think that's a bit better to see. So in fact, what you have is you have your constraints. So say this is your packing problem here. So you have 3 linear constraints. And now you have what you see here, everything is in log space, what you see here. So you see the objective function here on the left. And then there's this dark shaded area here where the optimal solution will lie somewhere. But the moment you leave the feasible region, of course, the objective function is rapidly increasing, which is what you expect from a barrier function. But the key point here, and some of the proofs explicitly use this later, is what happens with the gradients. Because if you look on the right-hand side, you see the gradients. Everything is transformed here back into original space so that you see what's going on. And what happens now is if you leave the feasible region and you're here, say, then even a tiny step will bring you back into the feasible region because the gradients are huge. They basically, like, I mean, everything's in log scale here, and you see like they immediately increase here, right? So they're huge and bring you immediately back into the feasible region. On the other hand, when you're in the feasible region, let's say here, the gradients are very, very small. So you can take huge steps without leaving the feasible region. And that really helps you basically, if you accidentally step outside of the feasible region, to immediately bring you back into the feasible region and basically maintain epsilon feasibility throughout. Yeah, so that's basically in terms of the barrier function that we're going to use today. Now we have to look at the second thing, which is actually the width independence. And that goes together hand in hand with the reformulation that we have seen earlier. Because after you've done the reformulation, it's actually quite easy to see that if you take a matrix A that is like rescaled as before, like this is say your A, and you look at an optimal solution to your one fair packing problem after the transformation, you will actually see that each of the optimal coordinates has to be at least 1 away. And that's super useful because now you can basically put a box around your feasible region and you know that the variables cannot be too small. And that's important because whenever you run like your favorite constraint optimization method, you typically have some dependence on the diameter of the feasible region or distance to the optimal solution. And that ensures that this distance is actually small, independent of A, and that is important to achieve the width independence here. So that's effectively the problem that we're going to solve here. We minimize this regularized objective such that subject to this bounding constraint. Again, the box is chosen a bit larger. It's actually not really constraining the solution. It's just there to ease some of the proofs, like in the mirror descent steps, you can immediately bound the regret that you get. Good. So having said that, one thing that is important that I need to convince you of now is that if you solve this regularized problem and you obtain an optimal solution, then this optimal solution is in some sense good enough to solve the original problem that we care for, so the one fair packing problem. So let's suppose that you have, let's say, an optimal solution x star r to this regularized problem that we see up here. Let's say x star denotes the optimal solution to the original problem that you care for. I've written it here in this exponential space, but this doesn't matter, that it's really just reparameterization. And then you have an epsilon approximate optimal solution to your regularized problem. Then the following things hold. So the first thing that you can see is that this optimal solution that you had here for the regularized problem, the true optimal solution, is a 3 epsilon optimal solution for the original problem. The epsilon dependence comes in because the barrier depends on the epsilon here, so otherwise this would not happen. Then the second thing that you can see is if you look at this epsilon approximate solution, then this solution is almost going to satisfy your constraint. So you have a very, very small multiplicative error on the right-hand side. And then what you can do is you can basically do a bit of a pullback. So you take this approximate solution that you had, you subtract a little bit of the all one vector. So you just pull it back a little bit into the feasible region. And then what you see is if you compare the value of that solution for the original problem with the value of the optimal solution, then this is basically a 5 epsilon approximation, and you satisfy your constraints as you were supposed to. So that tells us, yes, if we can solve this problem here efficiently down to epsilon accuracy, this will provide us with the solution to the original problem. All right. So that's in terms of with the independence and the reformulation. Now let's have a look at the algorithm. I would highly recommend just to ignore all that stuff up here. That's just parameter estimation that you do as part of the proof. You just see whatever you need to make things work. So there's nothing deep in there. Just see how to fit things together. Maybe the only thing that you want to see is that the t, the number of iterations that we do here, is basically really n by epsilon here. The rest doesn't really matter. So the setup is super easy, like as it is very often. You have an easy algorithm, but a complicated analysis. Let's maybe ignore the very first two steps for a second. Let's suppose that you have done a couple of iterations, okay? So you have three sets of points that we maintain. The first ones are these xk's. Let's call them attachments points. So these are the points at which I compute my gradients and things like this. Then I have my zk's here. These are my dual points. So they basically, I basically use them in dual space. I run mirror descent on those. And then I have the yk's here. These are my primal points. So suppose you have done a couple of iterations. You have obtained whatever, some attachment point xk. Then the first thing that you do is you do a mirror descent step. So what does it mean? I basically, I have my gradient here. In fact, we take the truncated gradient. We will see this in a second. And then I take it at this attachment point xk here. And I just do a standard mirror descent step. There's nothing fancy going on here. And I basically do this with respect to the feasible region B here. We have to talk a bit about the truncation here of the gradients, because there's a couple of things going on here. So anyway, so I first do this step. That's basically a dual update. Now what I do is I do a gradient descent step afterwards, and I do it in the direction of the difference of two of the iterates here. Okay? So forget about the learning rate and what the step size is. That's all not important. These are all things that you estimate after the fact. But there's a bit of magic going on here, because if you look at the step, you will see that this is actually not a projected step. This is a completely unconstrained gradient descent step, and these are going to be my primary solutions. So it turns out, just by the way of how the algorithm is built, you can do these unconstrained gradient steps without leaving the feasible region. And the reason for this is that in reality, you don't see this here, but in reality, the yk's are convex combinations of zk's only. And the zk's were feasible because you project, so they have nothing to worry about. And the xk's here, your attachment points, are feasible anyways because they're convex combinations of the primal and the dual solution. Okay, so that's basically what the algorithm does. You do a mirror descent step with a truncated gradient. Truncation is good enough because we had this nice property that it pushes you back into the feasible region. And then basically we correct that mirror descent step, because it was actually a relatively bad step, with a gradient descent step afterwards. And that step magically fixes everything that we broke beforehand. So that's the whole algorithm. And then, of course, you do like the usual setting here of nice constants to basically get acceleration. Not important. You do this after the fact.
Just to be clear, why is step number 9 a gradient descent step?
So it's actually like, I mean, it's a gradient descent step, but your gradient direction is the difference between these 2 points in dual space. So if this would be unconstrained here, this would be not constrained, and you take the distance, then the difference between these 2 points would be exactly the negative of the gradient. If you would not have a field.
And B is
just the box, just the box.
Oh, it's
just the box. It's two norm projections, so it's just clipping of the coordinates. But if you would leave the box, which you don't do. Okay. So, and if this would be unconstrained, right, the difference of 2 iterates is actually the gradient. So this is why I say it's a gradient descent like step. Okay. So it's like a gradient mapping type of thing. Not important. Good. So that's basically the algorithm here.
Quick question on the algorithm. Can you like
yes.
Number 3, it seems like if m is like exponential in n, then the number iteration could be.
Yeah, so it goes into the log factor, right? If you have an exponential m, you basically get a bit of probably a linear factor in that. Yeah. So that's basically the algorithm. Good. Now let's look at the respective steps. So as I said, we run mirror descent on the truncated gradient. That makes a lot of sense. If you know something about mirror descent, you have always the dependence on the size of the gradient. So truncating the gradients makes things nicer. And what we do is for something very simple. We basically just kept the gradient by 1. So if it's too large, we just kept it by 1. That's the whole truncation that is going on here. And then you obtain the following mirror descent guarantee. This is literally just the standard mirror descent guarantee with 2 minor changes. You don't do the last step where you do Cauchy-Schwarz. not so important. If you don't know what this is, why you would do this, forget about this, not important. And then the other thing is we have explicitly plugged in that the difference of two Z estimates, Z iterates is basically this term here by the definition of the algorithm. Otherwise, it's just the mere descent guarantee. For those of you, why do you do mere descent, or how does this generally work? You always come up with an inequality of that form here that you see. Then you basically add them up, you average them out, and then you take the average solution that will be good solution. That's how mere descent from this type of guarantee works. Now, if you look at this, these things here, these two terms typically will basically telescope out when you do this, because they basically go away. And then what you will end up with is this term here. So this is what actually drives the regret, because that's what you accumulate over your iterations, which is not telescoped away. And that's what you need to control here. And we control this effectively by having truncated the gradient on the one hand, but then also by a nice property of this gradient descent step that we will see in a second. So nonetheless, as you can see, we don't use the true gradient here, so we make some form of a mistake. And whenever we do mistakes, you have to pay for this at some point, which is exactly what we're going to do now. And this brings us to the gradient descent step here. So there's basically this descent lemma that you can see here. Let me tell you what it is. Don't try to parse it yourself. It's basically something that you can relatively easily derive from previous work from Diakonikolas from 2020. That was the n squared by epsilon squared algorithm. And that basically says that if you have xk and yk, so think of xk as your attachment point, and then fr xk minus fr yk, this is your primal progress. Your primal progress is lower bounded by 1/2 times the inner product of the gradient with these 2 points. So first of all, this is going to be non-negative. That's relatively easy to see because all the signs matches. But the other thing is it will be actually relatively large, and not relatively large. What you can show is this very nice compensation lemma here that says the following thing. So if we look at think of the mere descent step that we did beforehand. We made a mistake because we took the truncated gradients. Let's consider this error here. So the new k is literally the difference of the two gradients, like the real one and the truncated one. So that's our error term. And then this was the term, the regret term that we had on the right-hand side before in the mere descent inequality. So what this lemma states now is that if you take the truncation error, that's the first term, plus the regret that you accumulate, this is no larger than the primal progress that you made with the gradient descent step, right? This is the primal progress here of the gradient descent step. So what it tells you is, yeah, sure, I made a mistake by taking the truncated gradient, and I have to pay for the regret. But the mere descent step magically actually compensates for this. So it both gets rid of the error that you had from the approximation and also the regret that you had from that you would have accumulated otherwise. And these are the key properties to make everything work. And then I will spend now the last few seconds or minutes to talk a bit about the coupling and putting everything together. So let's see if we can prove that this actually provides an epsilon approximate solution. So what we do is we consider the gap with respect to this attachment point xk. Forget about the new case here. We were going to divide by them in the end anyways, but it makes it easier to write. So we have this gap here. We have basically fr at xk minus fr of u, and u is any other possible point that you potentially could have taken here. In the end, we were going to simply substitute the optimal solution, but for now, think of it as any possible point that you can take. So then the first thing that you can do is just by convexity, you can upper bound this in a standard way by the gradient term here. So nothing has happened. And now we expand that term to basically work with this approximation. So we have the error term here. This is just the error term for taking the truncated gradient. And then we have this term here that is basically arising now with the truncated gradient and to which we want to apply the mere descent guarantee a little later. So we have basically to deal with these three terms. Before we apply the mere descent guarantee, we quickly substitute the definition of xk. We could have also done this later. This is just for technicality to be able to rewrite the first term here and basically have it in yk minus xk and not in xk minus zk. So that's just technicality for now. And now we have this term here that we want to get rid of. For this term, we can now plug in the mere descent guarantee. And what you get is basically this regret term that we accumulate, plus these two terms here that are going to telescope away once we add them up. So you don't need to worry about them. They will go away anyways. But now we had the gradient descent step that is going to compensate both for this guy here, which was our error or our regret, and also our approximation error that we have here. So by applying this guarantee, I can get rid of these two terms here, which is exactly what we're going to do now. And now you're almost done. Like, I mean, sure, you might not see this if you have not seen this type of proof before, but if you're at this line, you're basically done. You just add up the stuff, you clean up the things, you average out, you're done. So that's exactly what we're going to do. Let me just clean this up a little bit for you, substitute a few more values. And when you then add up things, you end up basically with this type of inequality. So you have some accumulation of a constant factor on the left-hand side. Then you have the primal value at the optimal point. And then you have these other terms here. If you pay close attention, then you see that these other terms are basically measuring two distances. So the first thing that you have here, this is the original optimality gap in primal value, right? So this is basically y0, that was my initial point, and my optimal solution. And here I have the same thing, but just in the distance. So I have basically two error measures that depend on my initial distance, once in distance and once in function value. And then I have the value that I actually care for here. This is the FRYT, and I have the CT in front of it. So I can just rearrange everything, put it on the other side, divide by CT, and clean things up. And when I do this, I basically end up with this term. Honestly, nothing has happened here. We just rearranged things. So what you see now is that you have FR of YT, that's the function value that you care for. This is upper bounded by the optimal value, that's our reference point, plus some dirt. So what is this dirt here? So this is the primal initial gap that we had, plus the initial distance to the optimal solution with some constant factors that are in front of it. And now I still have the freedom to choose the CT, and the CT, of course, I've chosen in such a way that it makes this whole thing here to be less than epsilon, just by choosing parameters. And then basically you end up that the YT that you obtain at the end of the algorithm is an epsilon approximate solution to the optimal solution for the regularized problem. Then you apply the lemma, and then you basically get your 5 epsilon approximation to the original problem and a feasible solution. All right, that's all that I had for today. Thank you very much.